It is June 2026, and we are currently using, artificial intelligence to automatically analyze and rewrite legacy code bases across entire corporate portfolio.
Yeah, yeah.
But until this week, if an Azure virtual machine couldn't reach the internet through a standard V2 NAT gateway, you were fundamentally blocked from using the basic ping command to figure out why.
I mean, it really highlights the bizarre reality of cloud architecture right now.
Yeah, it does.
We have access to literal supercomputers on demand,
Right.
but we still hit these structural walls built around basic network routing and storage isolation.
Exactly. And breaking down those structural walls is our focus today. So welcome to this deep dive.
Glad to be here.
For those of you joining us, our mission is to examine the weekly stack of Azure service updates, specifically the ones from June 16 to June 17, 2026.
Yep.
And we want to distill exactly what they mean for your architectural designs, because we are speaking directly to you, the developers, the engineers, the platform architects building these systems.
So we are keeping the marketing fluff out of it.
Right. We are going to dive straight into the underlying mechanics of how these updates actually alter your daily engineering workflows.
Because looking past the standard changelog is critical.
Oh, absolutely.
We have to evaluate whether an update simply patches a UI bug or if it fundamentally changes how data is written, how code dependencies are evaluated, or how packets traverse a gateway.
And the updates we have queued up today definitely fall into the latter category.
They do.
We are looking at massive steps forward in data unification with Azure Databricks and Microsoft OneLake. We have the injection of LLM intelligence into legacy migration assessment.
That one is huge.
Yeah. And as I teased at the top, a surprisingly vital update regarding basic ICMP network traffic.
Finally.
Right. But let's start at the foundational layer, your data. Because before you can optimize your code or tune your application logic, you have to ensure your data architecture isn't bogged down by redundant storage silos.
Yeah, we have two highly connected updates here for the data layer. One is officially generally available, and the other is in public preview. And both target the operational friction between Databricks Compute and Azure Storage.
So let's lay out the facts. The generally available update allows Azure Databricks to have native read access to data stored in Microsoft OneLake through Unity Catalog.
Correct.
The documentation claims you can query and analyze directly without, moving or copying data.
Which is what everyone wants.
Right.
Yeah.
Building on that, the public preview update introduces the ability for Azure Databricks to natively write managed Delta tables directly back to OneLake.
Yeah.
And the stated architectural goal there is treating OneLake as a unified storage layer without requiring separate storage accounts.
So bringing those native read and write capabilities together, it changes the calculus for designing analytics environments.
Oh, so?
Well, it removes an entire layer of infrastructure management.
I am going to push back on that, though.
Okay, go ahead.
Every time a new data platform feature launches, we are promised this zero data movement idea.
Yeah.
But historically, when we get into the actual deployment, data lakes that promise zero movement still require complex extract, transform, and load pipelines.
Yeah, the old ETL trap.
Exactly. Or, at the very least, they require spinning up a hidden staging environment under the hood just to make the Kusto queries or Spark jobs perform properly.
Right, right.
So does this Unity catalog integration actually eliminate the need for separate storage accounts? Or is this just, another abstraction layer sitting on top of a fragmented backend?
That skepticism is totally justified, honestly, because virtualization layers often crumble under heavy concurrent querying.
Yes.
But the underlying mechanics here are actually different.
Okay, break that down for me.
So by allowing Databricks to natively write managed Delta tables to OneLake, Microsoft isn't just laying a virtualization mesh over existing silos.
Okay.
They are functionally removing the requirement to bootstrap a separate, disconnected storage backend for your Databricks workspaces entirely.
That is a massive shift from the old architecture.
It really is.
Because think about what we used to go through. If you needed a new Databricks workspace, the very first thing you did was provision a dedicated Azure Data Lake Storage Gen 2 account. An ADLS Gen 2 bucket.
Just for that compute to talk to.
Right.
And it was never just provisioning the bucket, was it?
Never.
You had to configure the virtual network peering. You had to set up the private endpoints.
The private endpoint.
And then map the role-based access control policies between the workspace and the storage.
Don't forget defining the lifecycle management rules.
Exactly. That is a heavy, heavy architectural tax just to get a blank canvas to work on.
Then if another service, or let's say another analytics team, needed to read that data, you were caught in a trap.
Yep.
You either had to copy the data into their specific storage account, which duplicates your storage costs.
Which finance loves.
Right, exactly. Or you had to build a complex sharing protocol that, quite frankly, often broke down when permissions drifted.
Yeah, permissions drift was a nightmare. So now, compare that to the mechanics of this new update. Because Databricks writes managed Delta tables directly to OneLake, OneLake operates as the native storage engine.
Got it.
And Unity Catalog serves as the control plane for governance and metadata.
So what happens when a cluster actually runs a query?
Well, when your Databricks cluster runs a query or writes a new table, it interfaces directly with OneLake's APIs through the definitions held in Unity Catalog.
Meaning the compute truly is decoupled from the storage.
Yes.
And without the performance penalty of traditional virtualization.
Precisely the point. You define your data governance policies once inside Unity Catalog.
Okay.
And then that data is immediately available to any other service that interfaces with OneLake. It completely eliminates the need to set up redundant ADLS Gen 2 accounts.
Or synchronize complex access policies across multiple environments.
Right. It accelerates time to insight because the engineering team isn't, waiting on the infrastructure team to build a new staging layer.
So Unity Catalog handles the governance, and OneLake removes the storage friction. But having a frictionless data layer immediately exposes your next bottleneck.
Which is?
The legacy code you were trying to point at it.
Oh, yeah.
I mean, a modernized data lake does not help you much if you are hitting it with monolithic legacy applications running outdated database drivers.
The compute layer has to evolve at the same pace as the storage layer, otherwise you just move the latency from the database to the application server.
Which brings us to our second segment, accelerating development and modernizing code.
Right?
We have an update here in public preview that merges two tools operating at entirely different scales.
This one is fascinating.
Azure Migrate is now integrating with GitHub Copilot Modernization.
Yeah.
And the release notes state this brings Azure Migrate's portfolio-level discovery together with GitHub Copilot's context-aware code analysis.
To deliver what they call at-scale code insights.
Right. But blending an infrastructure assessment tool with an LLM-based code assistant is an unusual architectural choice.
It is, but it solves a very specific migration bottleneck.
Wait, I need to synthesize how these two scopes actually merge.
Okay.
Because GitHub Copilot is fundamentally a tactical micro-level tool.
Usually, yes.
It lives inside your integrated development environment, and it operates file by file.
Right.
But Azure Migrate is a macro-level tool. It drops an appliance into your hypervisor. It maps network dependencies across hundreds of virtual machines and calculates hardware utilization.
Exactly.
So how does Copilot's line-by-line analysis apply to an infrastructure-wide discovery process?
It requires elevating Copilot out of the IDE and turning it into a strategic modernization engine.
Okay, how so?
Let's look at the limitations of a traditional Azure Migrate assessment.
Sure.
The appliance scans your on-premises environment and builds a map. It tells you that server A is talking to server B over port 1433.
Which indicates a SQL database dependency.
Right, and it gives you CPU and memory metrics. But the assessment is completely blind to the actual application logic executing inside those virtual machines.
So if Azure Migrate is scanning the hypervisor and finding port 1433, it's essentially using that network dependency as a targeting laser.
Exactly.
It finds the connection at the infrastructure layer, but it doesn't know how deeply coupled the application code is to that specific database.
That is the blind spot. Historically, to figure out the depth of that coupling, an architect had to assign a team of engineers to manually audit the code repositories associated with those servers.
It's brutal.
It's awful. They had to hunt for hard-coded connection strings, outdated authentication wrappers, or, deprecated API calls.
And that took months.
Easily. But now, the Azure Migrate integration takes that infrastructure map and feeds the context directly into Copilot modernization.
Oh, I see. Copilot is using that infrastructure context to parse the dependencies across the actual code repositories.
Yes, at scale.
Wow.
Instead of waiting for a developer to ask a question in an IDE, the modernization engine proactively scans the entire portfolio of code bases flagged by Azure Migrate.
Right, so it looks for those specific modernization blockers.
Yeah, it leverages the micro-level semantic understanding of an LLM, but applies it across the macro-level topology.
The resulting output changes entirely then.
Completely.
You don't just get a spreadsheet saying, move these 50 VMs to Azure.
Right.
You get an assessment that says you have 50 VMs, and to successfully modernize the applications running on them, You need to refactor these 14 legacy authentication patterns buried inside these 3 specific repositories.
Exactly. It automates the code-level discovery phase.
That's incredible.
It collapses what used to be a grueling manual auditing process into a fast, automated assessment, giving architects a realistic view of the technical debt they have to refactor before they can even start the migration.
That solves a massive problem for migrating legacy portfolios.
Yeah.
But what about the developers building net new architectures?
Good question.
Our next update focuses on greenfield development. The Azure Functions extension for Visual Studio Code has launched a redesigned Create New project experience.
This is in public preview, right?
Yes, in public preview. Microsoft is replacing the old multi-step quick pick wizard with a rich, visual, filterable template gallery.
You know, on the surface, replacing a drop-down menu with a visual gallery sounds like a minor UI tweak.
It really does.
But it actually addresses a significant friction point in the serverless development loop.
Anyone who has used the command palette to scaffold an Azure function knows exactly what that friction feels like.
Oh, yeah.
The old quick pick wizard forced you through 5 or 6 sequential prompts.
You chose the language, the runtime version.
The trigger type, the authorization level, and if you realized on step 5 that you wanted an event grid trigger instead of an HTTP trigger,
You couldn't just go back one step.
no. You usually had to cancel the entire workflow and start over.
It was so frustrating. Linear command line interfaces are great for automated scripts, but they are terrible for discovery.
Absolutely.
So by moving to a visual, searchable template gallery, the extension exposes the entire surface area of Azure Functions up front.
You can filter by Python or C# and visually compare the boilerplate scaffolding for, say, Cosmos DB binding versus an Azure Service Bus trigger side by side.
It reduces the cognitive load of memorizing command line arguments.
Definitely.
Whether we are talking about Copilot automating the discovery of legacy tech debt or VS Code visually accelerating the scaffolding of serverless functions, the underlying theme is identical.
Which is?
Collapsing the distance between what a developer wants to build and the actual running code.
So, you've written the new serverless functions, you've modernized the legacy code, and it is all deployed and querying your unified OneLake data.
Sounds perfect.
But now, your operations team actually has to keep the lights on.
Ah, yes, the real world.
They have to monitor the traffic, troubleshoot the routing, and maintain system health. Which brings us to our final segment focusing on operational quality of life.
These are the updates targeted at the engineers who get paged at 3 in the morning when the architecture diagram fails to match reality.
Exactly. Which brings me back to the update I mentioned at the very beginning.
The ping update.
The ping update. This is officially generally available. ICMP support for Azure Standard V2 NAT Gateway.
Yep.
The gateway now supports outbound ICMP echo request and echo reply traffic.
Meaning what for the uninitiated?
Translated from networking terminology, you can finally use the ping command from a private workload to validate internet connectivity through the NAT gateway.
I can hear the frustration in your voice.
It's impossible not to point out the irony.
I know.
We just spent 10 minutes talking about artificial intelligence assessing entire portfolios of application code, and we were simultaneously celebrating the fact that we were finally allowed to ping an external server.
It's pretty funny.
Why has basic outbound ICMP traffic been blocked on the standard V2 NAT gateway up until now?
Well, to understand why it was blocked, you have to look at how network address translation, specifically SNAT, functions at cloud scale.
Let's pull that apart. Source network address translation is the mechanism that allows private virtual machines to share a single public IP address to reach the internet.
Correct. When a virtual machine initiates an outbound connection, the NAT gateway intercepts that traffic. Right. It rewrites the internal private IP address to its own public IP, assigns a new source port, and records that translation in a state table.
Okay, that makes sense.
Then, when the external server sends the response back, the gateway looks at its state table, finds the corresponding entry, rewrites the destination IP back to the internal virtual machine, and forwards the packet.
But tracking that state requires protocols that have a defined beginning, middle, and end.
Exactly.
Like TCP has a formal three-way handshake and a teardown process.
Yep.
UDP, while connectionless, still relies on defined ports that the gateway can track.
Right. But ICMP, the Internet Control Message Protocol that ping relies on, doesn't use ports at all.
It doesn't.
Think of TCP like sending a package via certified mail.
Okay.
There is a verified sender, a specific recipient, and a signature required upon delivery. The Postal Service, which is the NAT gateway in this analogy, can easily track the state of that transaction.
And ICMP.
ICMP is like tossing a loose postcard into a mailbox. It is entirely stateless.
And tracking millions of loose postcards across a massive multi-tenant cloud gateway is computationally expensive.
It is structurally complex, especially when you factor in security.
Security's always the catch, isn't it?
Always. If a gateway improperly handles stateless ICMP traffic, it exposes the underlying network topology to security risks like TTL-based mapping.
Time-to-live mapping.
Right, where attackers manipulate time-to-live packet limits to map out your internal network hops and discover hidden infrastructure.
Oh, okay.
Microsoft, prioritizing security and performance for the TCP and UDP traffic that makes up 99% of actual application payloads, chose to drop ICMP at the gateway by design.
But dropping it created a massive blind spot for operations teams.
Huge blind spot.
If an engineer was trying to figure out why an internal application couldn't reach a third-party API, they couldn't just run a simple ping to test basic internet routing.
Yep.
They had to rely on cumbersome workarounds like TCP ping or trying to curl the endpoint.
Which only works if the destination server happens to be listening on those specific web ports.
Right.
Look, in the middle of an outage, engineers rely on muscle memory. Ping is the most universally understood diagnostic tool in networking.
It is.
Enabling outbound ICMP echo request and reply means the platform engineers have finally solved the challenge of tracking stateless translations securely at high volume.
So it restores that immediate micro-level validation of network paths without compromising the gateway's security posture.
Exactly.
So ping gives you that micro-level binary validation. Can server A reach the internet, yes or no?
Yeah.
But ops teams also need macro-level visibility. They need to understand aggregate trends, latency spikes, and system health over time.
Which is much harder to do at scale.
Right. Which leads us to our final update, which is officially generally available, a new Azure portal experience for summary rules in log analytics.
This changes the operational economics of managing high-volume telemetry.
So the release notes detail that summary rules enable the aggregation of high-volume log data at a defined cadence.
Okay.
The aggregated results are then stored in summarized custom tables to improve query performance and reporting.
Right.
What is the actual architectural mechanism driving these summary rules?
You have to look at the compute cost of querying raw telemetry.
Okay, let's look at it.
Let's say your unified OneLake architecture is generating terabytes of access logs, network flow logs, and application traces every single day.
Terabytes.
Terabytes. If an operations engineer builds a dashboard to display the average latency of a critical API over the last 30 days, the log analytics workspace has to scan billions of raw log rows every single time someone opens that dashboard.
And scanning billions of rows takes time.
A lot of time. A dashboard that takes 45 seconds to load during an active incident is functionally useless.
Completely.
Plus, querying that much raw data burns through compute resources incredibly fast.
So what do summary rules do?
Summary rules move that computational burden to a background process.
Oh, I see.
You configure a defined cadence, say every hour. Every hour, the summary rule automatically executes a custo query language, or KQL, query against the raw log data. It calculates the minimums, maximums, averages, and error counts for that hour.
Got it.
Then it writes just those calculated metrics into a brand new summarized custom table.
So instead of your dashboard querying 10 million individual log entries for a given hour, it queries a single row in the summary table that represents the aggregate metrics for that hour.
Exactly. The dashboard loads in milliseconds instead of nearly a minute.
That's a massive performance gain.
Furthermore, the new portal experience provides a streamlined UI to manage the lifecycle of these rules.
Nice.
By pointing your long-term reports and dashboards at the summarized tables, you get drastically faster query performance and significantly lower compute costs.
It also solves the data retention problem, doesn't it?
It really does. You can configure your raw, high-volume log tables to automatically age out and delete after 30 days to save on storage costs.
But you can retain the aggregated summary tables for years to perform historical trend analysis.
Exactly. It gives you the macro-level operational visibility you need without forcing you to pay the performance and storage tax of keeping raw data forever.
If we step back and look at the entire stack of updates from this week, a very clear narrative emerges.
I agree.
These are not isolated feature drops. They represent a systematic reduction of architectural friction from the storage layer all the way up to network routing.
Microsoft is actively targeting the bottlenecks that slow down engineering velocity.
Yeah.
They are identifying the places where infrastructure complexity distracts developers from writing business logic, and they are abstracting that complexity away.
We started by looking at how Azure Databricks and OneLake are achieving unified analytics.
Right.
By allowing Databricks to write managed Delta tables natively to OneLake, architects no longer have to provision redundant ADLS Gen 2 accounts, configure complex VNet peering, or sync role-based access policies just to get their compute talking to their storage.
Then we saw Copilot modernization integrating with Azure Migrate. It takes the infrastructure topology discovered by the hypervisor scan and uses it to automatically analyze legacy code bases at scale, turning a manual, months-long auditing process into an automated assessment.
We saw that same focus on developer velocity with the new visual template gallery for Azure Functions and VS Code.
Removing the linear constraints of the old command palette.
Yes. And finally, operations teams are getting vital diagnostic workflows back with ping support on the V2 NAT gateway,
while simultaneously gaining the ability to aggregate massive telemetry logs into lightweight, highly performant custom tables using summary rules.
The platform is absorbing the heavy lifting.
It is. It is handling the stateless trapping for ICMP traffic and managing the data governance through Unity Catalog so that your engineering teams can focus entirely on outcomes.
Which brings us back to that tension between the whiteboard diagram and the actual deployment.
Oh, yeah.
Historically, the whiteboard was an idealized fiction.
A nice dream.
But with these updates, the deployed infrastructure is starting to behave a lot more like the diagram. The lines connecting the boxes are getting cleaner, faster, and requiring a lot less manual configuration.
The technical debt required simply to connect services is shrinking rapidly.
Which leaves us with a provocative question to consider as you evaluate your own architectures this week.
What is it?
As tools like Copilot integrate deeply into infrastructure migration assessments, and analytics platforms like Databricks write natively to centralized storage like OneLake without any staging layers, are we moving toward a future where the traditional rigid boundaries between code modernization, data storage, and infrastructure management completely dissolve?
It's the question, isn't it?
Are we rapidly approaching a single, automated deployment fabric where the platform itself dynamically adjusts the infrastructure to support the code you write?
It's fascinating to think about.
It is something to keep in mind as you design your next deployment. Thanks for joining us on this deep dive, and we will catch you on the next one.